In this video, we will be discussing high conductivity materials versus low conductivity materials and what test frequencies work best for sorting two high conductivity materials from each other and what frequencies work best for sorting two low conductivity materials that are on the low end of the conductivity spectrum. So I've set up a couple instruments here. The one right in front of me is the Workstation 2000 from Staveley Instruments. Probably my favorite tester. Anyway, I have a, let's see, where did I put it? Where does this cable go to? I got so many cables, so many probes around here. This is a 2 megahertz, 1 to 2 megahertz pencil probe, very tiny coil. And I'm operating at 2 megahertz. I've already set up a conductivity curve using this vintage Nortec conductivity sample. Ferrite, you can barely see it, but it's vectored up. 304 stainless, copper nickel, magnesium, 7075 T6 aluminum, 7075 TAC 0 aluminum. And last but not least, copper is right down there. And I never knew how handy this 20th anniversary Zetec 99.9% silver memorabilia coin would come in handy, but I need some silver here. How does the silver compare to copper? It's just about right on top of it. Let's try that again. What if I wanted to separate copper, of which I just happen to have a bar here, and a thicker sample. But let's just try the thick sample of copper here. Look at that vector. Now let's take a look at the 99.9% pure silver Zetec coin. They're both like 100% or 101, right? You can't distinguish the two, right? So obviously high frequencies do not work for separating two high conductivity materials. But what the high frequency does work well for is separating the effects from two low conductivity materials. And for this example, again, I'm going to look at the slide rule. I'm going to pick titanium because that's what I have here. And also maybe a 304 stainless because those are two on the low end of the conductivity spectrum. So remember, these are two high conductivity materials, copper and silver, right on top of each other. You can't tell the difference between the two. They look like the same material. But watch what happens when I use a high frequency and test two low frequency materials or conductivity materials. So this is titanium 1.09% IX. Okay, that's up there a ways. And then I'll use 304 stainless. You're not going to have any trouble telling that material from that material. 304 stainless, titanium. I mean, they're not that far apart, but they're a lot farther apart than the silver and the copper. Like, what if I touch some other materials? What about copper nickel? You know, that's not super conductive. What is copper nickel here? Copper nickel, I'm looking at the slide rule. Yeah, it's only 8% IX. So let's do that again. Copper nickel, titanium, and what was the other one? 304 stainless. These are three distinctly different impedance positions. But just to recap, if I compare the copper and the, I don't want to lose this thing. I paid $100 for it. They're right on top of each other. So to separate high conductivity materials, you need a low test frequency. Now, moving on to the second part of this demonstration, we're going to use everybody's favorite, the Nortec 600. Right? Okay. Now this one we have calibrated just a tad differently. Now where's this program? Pull on the cables because I got so many cables here. So many cables. Here I hooked up a Hawking, later known as GE, later known as Ether NDE. I got one of their probes. I wanted to get a larger probe. Wanted to drive it at a really low frequency. What frequency am I running exactly? 10 kilohertz. So what do you think we're going to try to accomplish with this low frequency, larger coil? We're going to be trying to separate indications from those high conductivity materials that we couldn't do with the high test frequency. So first, let's see what happens when we compare titanium. First, I got to erase the screen. Titanium, look at that, I can barely see it. And then what's something else that's low? Look at the slide rule. Titanium's 3%, 304 stainless, right? So my 304 stainless, I'm losing everything here. 304 stainless is gonna be right here. I'm guessing there's not gonna be some huge change. I mean, the separation angle is only like a few degrees. Now granted, I get a little bit more amplitude on the 304 stainless than I do on the titanium. But you know, what if I'm dealing with different thicknesses and stuff? I mean, it's just not that much difference between those two. What else do I have that's low? That's a lower, that's some sort of steel. That's real high permeability steel. Touching all sorts of stuff here. Oh, that thing I just touched right, where was it? There you go, there's something highly conductive. Anyway, I digress. Let's just go and try to separate the variables from two high conductivity materials. Let's just try that copper and the silver, because we couldn't separate them with the high frequency, right? So let's try 10 kilohertz on the copper. All right, that looks good. And we'll try the silver. I didn't give this a trial run, so I'm not sure how it's going to work, but it'll probably be separated more than it was with the 2 megahertz. I stand corrected. Still can't tell the difference between those two. Shucks. All right, well, let's try to separate copper from, how about pure aluminum? That's somewhat close, I guess. I mean, those are two distinctly different impedance points. There's a different type of aluminum. So clearly, you know, I can tell the difference between the lower conductivity materials or the higher conductivity materials when I use a low frequency. But when I try to separate low conductivity materials, like this titanium, and then 304 stainless, you see there's not much of a difference there. So if you wanted to sort those two out, you go back to the workstation and run the 2 megahertz. All right, I hope you enjoyed this lesson. End of today's lesson.